Okay, welcome everybody. Thanks for turning out. Everybody's, you know where you are, right? Because I wasn't expecting this kind of turnout. I really appreciate this. Everybody's here for managing networks in a software-defined future. Okay, how many people here work with SDN? Really? Okay. How many people want to work with SDN? Because it's a cool buzzword or because it's actually a thing? Yeah, okay. How many people here are already network people? All right, so pretty good subset. Awesome. And how many know already about the network management discipline, as we do with OpenNMS or with a tool like Netcool or OpenView, Node Manager, those sorts of things? Yeah. Who said FCAPS? You. Awesome. All right, you get extra credit. That's actually going to come up in a minute here. Good afternoon. This is a brief tour of what my talk's going to be about, a little bit about me. We'll talk about what old school networks looked like and still do. We'll talk about what the SDN future is alleged to look like. We'll talk a little bit about a case study that I've done using just some freely available open source SDN components, cover some conclusions, and I'll take some questions. So let's go. Who's this guy up in front of you? That's me. I've been around the industry for a while. I've managed some large-scale IP networks. I've written and consulted on a lot of different network management platforms. Most recently, I work with the OpenNMS group. Any OpenNMS users in the house? Go ahead, be proud. Awesome, we got one. Cool. Excellent. Well, OpenNMS, I'll just go ahead and put the spiel out there, is the world's first enterprise-grade network management platform developed under the open source model, which is a mouthful, and I'm not going to delve into all the details of that. Suffice it to say, it's really free, really open source, and it's been around for a really long time, 15 years, which is pretty long by open source software standards. Talk a little bit about what is in your old school network, classically speaking. You got switches? Right? I'm oversimplifying all of this pretty greatly, so please hold your comments until I get through this section, because I know that I'm being too simplistic about what these things do. Switches at base are all about switching your layer 2 frames, right? They're moving Ethernet frames in and out of interfaces. Very simple rules. They run spanning tree protocol to avoid loops in your topology, and that's pretty much what the job of the switch is in a classical network. They tend to have a lot of physical ports. Depending on what kind of switch they are, they'll have more or fewer. They're often modular devices with modules that you can plug in and out. They tend to have a very high throughput data plane because they tend to be heavy data moving machines. And their control plane is, classically at least, driven by a configuration that's stored locally on the device. Does that make anybody a little bit uncomfortable or angry? Yes? It's great. Who said that? Get out. OSPF is a problem. All respect to Mr. Dykstra. May he rest in peace. After your switches, you got your routers. We're going up the stack a little bit. How many here don't know about the 7-layer burrito? Okay. It is totally delicious. Routers at base are for moving your layer 3 IP packets around, or IPX if you're really old school and crazy, or what have you. Anything routable, a router will route it. This ain't woodshop, kids. You can run OSPF, you can run other routing protocols and so on your router. But yeah, at the end of the day, your routers are basically making decisions about whether your layer 3 packets are going out this interface or out that interface based on some set of rules. Router tends to have pretty few physical ports. They are often modular, but compared to a switch, the ports tend to be fewer in number. The backplane is a little bit less performant than a switch, just because they tend to be placed closer to the middle of the network and have a different job. The control plane on these things, in these routers, we've got a couple, I think we've got a total of 3 seats open up here. If you want to slide in, I won't be offended. We got one over there. Cool. Just like with your switches in the classical old school networks, guess where the configurations on your router are stored? They're stored locally. Yay! 2 exclamation points. Who's getting angrier? Cool. And then I'm using firewalls as a way oversimplified thing to stand for load balancers and everything that resides above layer 3 and wrangles packets and other data there. Their job is to move layer 3 packets around or higher layer things, but ultimately we're talking layer 3 packets, subject to a rule set. And of course, they get blamed when anything breaks because people don't really understand what's going on once you're above layer 3 at all. A lot of people try, and some people actually do, but those people are savants. Compared even to routers, these kinds of devices tend to have fewer physical ports still. Most of their interfaces tend to be logical, right? You guys have these in your networks. Low to medium throughput data plane, they're just doing a different kind of job, and that suits them just fine. The control plane on these things, even though probably with your firewalls you're configuring your rules through some centralized console and pushing them out, guess where the rules actually live? On the device. Pitchforks, people, get them out. All right. So on top of all of this anger that we've got building about the way we configure our classic old school networks, we've also got this problem of inventory and configuration management. This is really an attempt to work around the problem that your configurations are stored locally on the devices by centralizing some notion of which configurations and which versions of those configurations should be running on which of your devices. It helps, right? You want to make sure that the right configs are running on the right devices. Also, another job of your configuration and inventory management is to account for what's in your network. So how many routers do I have out there of type X, how many switches of type Y, and so on. Another job that inventory and configuration management does is to eat a lot of time and money. It's actually a really hard problem to do configuration management or inventory management. Big respect for people who do those things. I don't. Don't got time for that. Who's got time for that? Yeah, ain't nobody got, exactly, there you go. Ain't nobody. But typically, even your best configuration management systems have no real intellectual understanding of what the configurations are doing that they're pushing out or ensuring are running on the right devices. Your configuration management system doesn't really understand what it means that you've got your OSPF area 0 and then this other OSPF area. It just knows that this config goes on this device. There's no real smarts there. There's no centralized control of how your network is programmed because it's kind of not programmed. Also, even if you got a good inventory management system, are you sure that all your nodes are in there? How many people have an inventory management system? Are all your nodes in there? Exactly, you think. So maybe they are. More old school network components. We've got network management systems. That's what I do, OpenNMS, network management system. Not just about networks necessarily, but we're talking here today about networks. The bit plumbing that makes your enterprise go. You said FCAPS earlier. You get a cookie later. FCAPS is the OSI model for describing the management put into 5 pieces: fault management, configuration management, accounting management, performance management, and security management. Fault and performance are really the 2 things that OpenNMS, which is the platform I work on and consult on, is strongest in doing. The rest of those things are kind of not so much our thing because they're so hard, and a lot of other things do them very well, so we tend to integrate with other products that already do those things well. We do adhere roughly to FCAPS, and the way we implement FCAPS is really a 4-tiered approach. We have a provisioning subsystem, which is concerned basically with getting your nodes, interfaces, and services into management, how we become aware of what's in your network. We have a CERT, which is how we know whether services in your network, the things that people actually count on your network and the systems attached to it to provide, are performing. That's sort of like, is it answering a ping? Is it answering an HTTP GET request? Is it responding when I connect on port 22 and send an SSH client identifier after the server answers with a banner? Basic questions about, is it up or down? Also, fault management. This is how we take in events from outside the system. The classical way is via SNMP traps. We can also take in events via syslog, and a couple of other transports. TL1, who has TL1 experience? Oh boy. All right. One telco wonky person. Yep, been there. And then finally, we've got performance management, which is how we quantify anything that's trackable as a time series metric on a device or one of its child elements, like an interface or a CPU. Like how many bits have you pushed through that interface? How busy is that CPU? How much of your memory is utilized? That sort of information. That's performance management, or PM. And we do a lot of this stuff, all four of these concerns, really, through SNMP. Who knows what SNMP is? Yeah, it's not for sending email. How many people know what SNMP is? Yeah, that went down a little bit. Okay. Right, it's not SMTP, it's SNMP. Simple Network Management Protocol. Widely believed that the simple is a joke. A very cruel joke inflicted on people who try to implement agents, implement managers, and understand the workings of SNMP. It's called simple because in the original implementation of the protocol, there were only 5 verbs. So it was simple compared to, who remembers CMIP? Telco guy's going to laugh at this point. You remember CMIP, sir? Oh, okay. Then you didn't live through the wars. Neither did I. I was too young for that. But yeah, it was the competing management stack from the OSI. SNMP is the management framework from the TCP/IP side of the world, widely considered to have won the manageability wars in the 90s. At base, SNMP is about making requests from the management platform to the managed agents or the managed systems which have an agent running in them. Those are GET and GET bulk SNMP PDU types. There's also managed node to network management system unsolicited messages, or traps. You guys have worked with SNMP traps, most of you probably, if you've got SNMP in your network. Yeah, they're kind of a pain, but they're nicely structured data. They're easy enough to digest if you've got a platform that's good at digesting them. In this old school network paradigm, your routers, your switches, and so on are really where the action happens. That's also, as it happens, where the SNMP agents live. That's what the network management system talks to. So it talks directly to typically UDP 161 on your router, gets the data out, or the traps come directly from your router from whatever port to UDP 162 on me. That's how it works. We're talking directly to the leaf node in the network. And we can gather pretty much anything. We can get interface traffic, we can get BGP statistics, environmentals, stuff you haven't yet imagined. It's all pretty flexibly modeled with SNMP, and it is an extensible framework for describing management. We have this concept of a management information base, or MIB, not Men in Black, that lets SNMP be pretty much infinitely extensible as long as the data is not too complex to model. And we'll get to that. So here's your summary. This is what an old school network is, right? It's a bunch of sort of independent sovereign nodes running around. You kind of wind them up and let them go, and when you're lucky, the traffic probably goes where you meant for it to go, but sometimes you don't get so lucky because either you screwed up or you had a link drop out or something else happened that you couldn't anticipate. It's really, really hard to simulate a large-scale network. Anybody ever tried? Run like a network simulator? It's not easy. GNS3, exactly. That's about as close as you can get. It ain't perfect, right? I mean, it's not. It's like trying to draw a one-to-one scale map of your kingdom. Switches in 802.1q and GNS3, no thank you. No, it doesn't sound very fun at all. This is clearly not designed by hackers. It's pretty much untestable. So what are we going to do about it? Let's talk about the elements of software-defined networks. Let's take a question break if anybody has questions about what I just laid out. Cool. All right, moving. SDN. All right. For those people in here who have not done any SDN stuff or haven't really learned any SDN stuff, pay attention to this slide. If you leave here with just one fact on your mind, it is this. Software-defined networks is about the separation of the control plane, which is where the decisions are configured and made, from the data plane, which is where the data is actually moving around on your network. And it's also about programmability. That make sense? Cool. All right, in the software-defined networking world, all of these things, whether they're what we used to call a switch, or what we used to call a router, or what we used to call a firewall, or a load balancer, or what have you, they're pretty much all called a switch now. Just simplify the terminology a little bit. Their job is more or less complicated, but they're basically just moving frames or packets around, same as your old stuff did, just not without the rigid separation of roles always. The rules that govern this stuff come from a controller. So these guys implement the data plane, right? Switches are the data plane now. They're running on comparatively generic hardware. Usually they're ASICs in there that are better at switching or better at routing or better at layer 4 through 7 stuff, but they're pretty generic. And you can kind of tell a switch what it is. Are you switching stuff mainly, or are you routing stuff mainly, or are you doing some of each, or are you running routing protocols, or doing something we haven't imagined in the network world yet, which is the exciting thing. Sometimes your switches are virtual. They can be running in like KVM guests, like that's what Nexus is on Cisco Nexus platforms. They're KVM guests inside a Linux box. Pretty cool. And again, these things are called switches, no matter what they're doing. You just call it a switch, it seems. And by the way, I should have said earlier, in 3 months, everything I tell you is going to be obsolete because this world is changing really fast. I think purely imaginary networks. Sometimes I worry, honestly, as an aside, that we're building this tipsy tower of technology that's just going to fall over one day. But yeah, maybe not. I mean, I think the next thing is probably to Dockerize your software-defined networks. I think that's the next squaring of the buzzwords. And probably Kubernetes in there somewhere, I don't know. Right, so that's our data plane. It's switches, they're pretty generic. Now you got your control plane, or your controller, as it's often called. Your controller, guess what? It controls the behavior of your switches, or your data plane. The rules for doing this are centrally controlled and managed. You can probably put them in GitHub if you're into that kind of thing. Across nodes that are switches, I should have said switches instead of nodes there, that actually register to your controller. So guess what? Now you know everything that's in your network, because if it's not registered to your controller, it ain't moving data around, because your controller has to know about it in order to tell it what to do. In addition to all of this, the controller also exposes your inventory, configuration, and other facts about your network via a set of allegedly open APIs. That's shifting a little bit. You know, Cisco was all about open flow and programmability, and then they kind of backed away from that because they realized that might jeopardize their favorable position in the market. So, yeah, I'll repeat that. A lot of the established, entrenched vendors feel pretty threatened, it seems. Don't want to put words in their mouths. If there are any vendors in the room, I can't speak for you, but if you're out there, you seem to feel a little bit threatened by this stuff. How much do I embrace it? How much do I fight it? Yeah. The question is that because this is commodity hardware that we're dealing with? To a large degree it is. How does somebody, let's just say, aren't they going to customize their own software regardless? Yeah, it's just going to be harder if this world comes to be the way it's described here, to differentiate yourself on just like, I don't know, throwing a picture of a bridge on the side of the thing and saying, buy it because bridge, or a flower, and buy it because there's a flower on it. And the vendors I'm referring to there, if you don't know who they are, look it up. What I'm getting from this gentleman in the front is his understanding is software-defined networking is basically all about routing with your switching done internally. Yeah, it's routing, switching. It's really just blurring the boundaries among the layers so that a given switch in your network isn't necessarily tied down to a single role. It can actually be making decisions at lots of different levels in the 7-layer model about what to do with the data that's flowing. Right. Yes. So I'll repeat that for the recording. The intelligence is coming out of the switch where it used to be configured locally and going into the controller. It's centrally configured now. And yeah, go ahead. It is partly about performance. Hardware has gotten good enough that the switch can be pretty dumb and just get its marching orders from a controller. I think another part of it is just about the move towards sort of a more agile way of running things. Sort of, you could credit the DevOps mindset with a lot of this. I think let's build things that are repeatable and testable, and even if they're distributed systems, can be centrally configured. Yeah, that's kind of what's going on here, and that's a lot of what threatens the vendors, or seems to have the vendors feeling threatened, who are entrenched in this space, is just that if everybody's stuff is more or less the same, how do I make myself look good and continue to dominate this market that I've dominated for the past 30 years? Right, by commodity hardware, yeah, do you have Cisco Nexus stuff? Do you know somebody who does? Juniper, yeah. So Cisco Nexus, it's just Linux boxes. They're big fancy Linux boxes, but they're, correct me if I'm wrong, but they're x86 64 boxes. They've probably got fancy ECC memory, but yeah. Yeah. What is? Cumulus. Yeah. That's not something I'm familiar with. Cumulus meant something different back in the 90s, but I don't think it's the same thing. Ah. Right. I'm going to summarize that for the recording. Basically, instead of millions of lines of code in OSPF and similar routing protocols figuring out how your networks plug together, you can have just hundreds of lines of code running in your SDN controller, and that's pretty cool stuff. Yeah, so, and at base, inventory configuration, and I got carried away there. But another function that the SDN controllers are meant to provide is scripting hooks, so that you can program your network in custom ways that the vendor never imagined, which is pretty neat stuff too. And the controller, as we already discussed, just like the switches, really, it's just a general purpose computer. It's just a server class machine. It might have a bridge on it or a flower on it, depending on which vendor sold it to you, or you could just roll your own. Question in the back? Right. So I'll repeat the comment/question. Yeah, it's a general purpose computer. Does that mean you can virtualize it, implement high availability pairing? Yep, absolutely. That's a thing. Yep. So question is, since we're talking about commodity hardware, can we just like buy a server class machine, plug a blade with a crap load of Ethernet ports onto it, and make our own switch? Yes. In theory, yes, absolutely. And my case study will, I think, show you how you would do that if it's something you wanted to do. Yeah, you can virtualize this stuff. It's pretty neat. So in summary, instead of a bunch of wind-up robots, we've got something that looks more like a migrating flock of birds. It kind of makes the decisions in a flowing fashion based on rules. Well, okay, these rules were built up over millions of years of evolution. Hopefully, we're going to spend at least a few hours programming our controller to make our network work the way it wants to go. It's made up of relatively dumb switches. We've got central configuration and inventory management. We've got programmability. And guess what? Now, instead of luck, it's mainly a question of skill, whether the network works the way you intended for it to do. Mm-hmm. Question is, what do I mean by luck about hoping that your old school network works together properly? Um, if you're configuring an old school network with configurations that are running on each device, and you don't quite understand how things work together, like if you have the wrong OSPF area configured on this router versus this one, it's never going to converge into that area. So little mistakes are very easy to make at different points in your network. Right. So yeah. Hmm. That's the idea. So instead of right. Right, yeah. So in the old days, and I should point out this guy says he's studying for his CCNA, which is awesome. I applaud you. Good job. I'm a way lapsed CCNA myself. It's a fun cert to get. It's been a while for me. Yeah, instead of a million distributed configurations, you've got a more centralized one that has a lot of other implications too. Instead of having to get a change window to push a configuration change, you just need a very short window to change one configuration in one place if you want to reprogram your whole network or break it, right? But it's much more about skill now than about luck. Yeah. If the controller fails, what happens? Does it just get frozen in time? Honestly, I don't know. I think probably that the switches keep running with whatever configuration they last had if they become disconnected from the controller. That's I am. Right. Right. So OpenFlow has the notion of active standby pairing baked right into it. But you do have to have a standby controller if you want to have that fault tolerant capability. Right. So maybe that's the way that the vendors make more money, sell more standby units. Yeah, so we're controlling things in this new centralized yet distributed way. Guys, we might even be able to unit test our freaking networks. How cool would that be? Yeah, pretty awesome. This is how hackers would like to build networks, I think. So I'm pretty excited about building networks this way, or at least seeing people build them this way. So I got a case study. Before I dive into the case study, does anybody have other questions that you'd like me to address? Okay, time's up. So for this little case study, I don't have a giant lab full of expensive equipment from vendors that put bridges and flowers on things. So I just grabbed for open source implementations of an OpenFlow stack. For the SDN controller in this case study, I used Project Floodlight. Anybody worked with that? Yep. Floodlight implements OpenFlow 1.0 through 1.4. It's an Apache licensed open source project from Big Switch Networks. Their play seems to be getting OEMs to have them help customize Floodlight downstream as, say, a brand X controller. You can visit them at projectfloodlight.org. It's actually, for somebody like me who wrangles Java on a pretty daily basis, it's really easy to build Floodlight and get it up and running. It's virtually brainless as long as you know how to type ant and then run a shell script. That's it. That's all that's required after you check it out of their Git repo. Really, really easy. I was impressed and surprised. That's the reason my slides are actually done today. For my switches in this case study, I chose Open vSwitch. Who's worked with Open vSwitch? Yep. So Open vSwitch implements OpenFlow 1.3, I think, right now. I chose Fedora 21 just because I like Fedora, and 21 is the newest. Just like the Project Floodlight controller, Open vSwitch is an Apache licensed project. The maintainership, I haven't been able to figure out who exactly. I think a company called Nicira started the Open vSwitch initiative. They were bought by VMware, but I don't think VMware's really turning screws and pulling levers in Open vSwitch as far as I can tell, or are they? Okay, so VMware seems to be paying some developers. Cool. Right. So the comment is there's funding for an internal VMware effort, their own implementation of Open vSwitch, but also the outward maintainership from within VMware. But there seem to be maintainers from outside VMware also contributing to the project. And there have been kernel space implementations in both Linux and FreeBSD, and user space implementation in NetBSD. I think that's newer. Probably not quite as efficient as kernel space, but hey, what do you want? That'll probably get into OpenBSD eventually, and they'll be happier because it's not in kernel space. You can check these guys out at openvswitch.org, but if you've got a recent Linux distribution, you can probably just yum or apt-get install Open vSwitch, and you've got yourself the makings of an SDN OpenFlow speaking switch right there on your Linux box. You can create a bridge, add an interface to it, and register it to your floodlight controller, and you're off to the races. Mhm. Okay, so if you want to play around in a university-type space, Mininet is an awesome network simulator that makes it even easier and more brainless than setting up Open vSwitch and Project Floodlight. All right, so here is what I found in my little case study. For the provisioning and inventory concern, there are really two options for how we could approach this if we want to build an integration between, say, Project Floodlight and a management platform like OpenNMS. Option one is reprogram the controller so that it pushes its inventory into the management platform. In this case, we have a REST API for controlling OpenNMS's inventory. There are actually two different ones, depending on how you want it to work. This option leans heavily on the internal programmability of the SDN controller. I found in my dorking around with Floodlight that it's probably not quite as scriptable as we'd like yet for this kind of purpose. You can run apps on Floodlight, but I couldn't quite puzzle out, despite being pretty good at puzzling out these things in general, exactly how I would implement this kind of thing. But we'll talk about it more in a second. And then option two would be to pull in the other direction, use OpenNMS or a thing called PRIS, which is a sort of adjunct for provisioning, to pull the inventory out of the SDN controller via its REST API. That, of course, leans on the strength of the SDN controller's API, which in the case of Floodlight seems to be a little bit better than its programmability. So, push mode. Who reads Java? There's not much, I promise. It's mostly comments, really. Inside Floodlight, there's this Java interface called iNotification Manager. It has a single method, which is post notification. That gets called when a switch registers to the controller. You just send a string. It's basically a logging method. Right now, the default implementation of that class, all it does is just squawk to syslog. It just writes a message that ends up on your standard out or in your syslog logs on the system. So if we were going to do this pushwise, the first step would be to write a new notification manager implementation, which would be fully supported. It's designed to be overridden by new implementations. And one that would, say, make HTTP posts to OpenNMS's provisioning requisition REST endpoint. Pretty straightforward to do, pretty well understood. Not going to go into it in depth because of time. Or if you wanted to go cheap and cheesy, you could just watch the logs as they accumulate. Write a little script that checks the logs once in a while and says, I see a switch got added. Here's the switch's DPID. Who knows what a DPID is, by the way? Data path ID. It's basically, looks like an 8-byte identifier for a switch in an SDN. So just have your little script. Do the same post to the OpenNMS REST API. Boom, your node's in, and we can start managing it. Doesn't seem to be really the cleanest approach, but it should be pretty effective. If somebody wanted to try it, that'd be awesome. Any people who hack on Floodlight or another SDN controller, any of those people in here want to comment? Um, that's what made me choose Floodlight. The documentation on the REST API is good and works. Some other controllers are available, but the documentation may not be quite as good or work quite as well with this gentleman's way of digesting information. Let's put it that way. Mine too. We think a lot alike. Okay, so that leaves us with option 2, pull mode operation, in which case we somehow, from the OpenNMS side, probably through PRIS, which is the provisioning integration server, it's actually a separate project that started life as a Google Summer of Code project and now has taken on a life of its own. It's basically a piece of middleware that knows how to talk drivers to any kind of a backend and present requisition XML documents to OpenNMS that tell it, here are the nodes and interfaces that you need to be concerned with. We would just write a, sorry, my cursor's creeping. We would just write a PRIS plugin, a source plugin it would be called, whose job is to go talk to the switches endpoint on the Floodlight REST API. So this is the output. I just spun up a couple of Open vSwitch nodes, switches, and a Floodlight, and just started crawling the REST API on the Floodlight controller. This is what I get. So you can see I've got 2 switches, Wash and Zoe. They've got different data path identifiers. You can see how long they've been connected, not very long, and we get to see what their IP addresses are. That's all the information that you need. Brown coats in the house? Yes, good. Guess what the, yeah, you see what the name of the controller is too, thanks. Yeah, so that's all the information that you really need to provision a node into OpenNMS. That was, by the way, just our list of all the switches, very basic information, just enough to identify it and know its IP address. Yeah, question? That is the port, the source port for the connection that originated its registration to the controller in the current session. So if it, that's the source port of the TCP connection to the Floodlight controller's port 6653, which is now the standard OpenFlow controller port. That'll change if the device disconnects and reconnects, probably. Yep. Well, these are actually not MAC addresses. They may be based on MAC addresses, but they're actually 8-byte identifiers. I haven't dug into exactly where they originate from. They may even be quasi-random, but I'm not sure. Do you know? Oops. Comes from the OpenFlow standard, so consult the RFCs. Yeah, they may be MAC address derived. Yeah, probably kind of like the IPv6 stateless configuration, similar mechanism to that maybe. So not exactly sure where those come from, but the question at base was, everything is pretty hard-coded here. This is actually what comes out of the controller's REST API. So if I connected another switch to the controller and asked for exactly this same HTTP URL against the REST API, I would get the same stuff plus the information, the basic information for the additional switch. So this is updated on the fly, as far as I can tell in real time, maybe a few milliseconds lag tops probably, by Floodlight or whatever your OpenFlow controller is. And this should be part of the OpenFlow standard APIs, I believe. I'm getting a nod. Furthermore, if we want to dig into more details about a given switch, well, we just ask for a slightly different endpoint whose URL includes the data path identifier of the switch we're interested in, ask for its description in JSON format, and we get this very useful stuff, which probably would be a lot better if we had like a Cisco Nexus 1000V or some other kind of fancier thing that's not just a Fedora node running Open vSwitch. It would probably have a serial number that's something other than none, and a data path description that's something other than none. Guessing data path description would be like a name for the node, like Zoe or Wash. No, like this guy. That would normally be like the host name of the thing, probably. Yeah, I don't know either. I'm hoping that it would be something like Zoe or Wash in this case. Yeah, so this is a bit short on details. That's really on Open vSwitch for not providing a whole lot of information, and on me for not getting an earlier start on these slides and actually digging up a real vendor-supported device that provides richer information. Anybody with Nexus or Arista or Cumulus or other OpenFlow capable switches wants to play around with this kind of thing and let me know if you get better data. Love to know what you get out of this API endpoint. We can talk later. Right, so we can also find out about the ports on a given switch via the REST API. So just a slightly different URL again. There's the data path identifier for the switch we're interested in. In this case, it's Zoe again. We ask for port desk and JSON. So this is the description of the ports that are available on this switch. In this case, we've got 2 ports. We've got the ETH1 port and the local port, which is, I think, the parent node itself, or the main bridge that ETH1 belongs to. We can see the hardware MAC address of these 2 interfaces. We can see the current speed and maximum speed. In this case, it's running at 1 gig. Its max speed is 10 gig. That looks a lot like the stuff that's in the if table for people who are familiar with SNMP already. So we can use this in a similar way to the data that's in the if table. Beyond the port descriptions, we can also get, oh, sorry, I'm getting ahead of myself. So that really is all we need to build a requisition for OpenNMS. Who's built an OpenNMS requisition? Awesome! You get a cookie too. 1 guy. 2 guys in the room now. Let's talk later. I want to hear about them. All the weird things you've made OpenNMS do. Yeah, so simplest case, we just build a requisition using a Pris source plugin that's yet to be written, but really simple to write. We use the data path ID of the switch as the foreign ID of the node in the requisition. Here's Wash. His foreign ID is his data path ID. We know his IP address because it was in there, right? So there it is there. It's the SNMP primary interface, because we're still going to speak SNMP to the switches, I think, probably, for the time being at least. And there's Zoe. She's got a different foreign ID, so she's going to come out as a separate node. The only thing that's really a dangling end in my mind with this right now is how we find the node labels. I think that's probably what's in that data path description field when you're dealing with actual well-thought-out hardware that's not just a Fedora instance that I spun up on EC2. Right. Yeah, so there's supposedly a successor to SNMP called netconf. I don't know if it's in the schedule, but the subtitle of this talk is, "And is SNMP finally dead?" Is that in there? That, okay. Wow, I figured that was what got the rest of you into here who weren't just buzzword operated. Yeah, people have been predicting the death of SNMP for a long time. But we'll talk about that in a few minutes. netconf, I don't think, is going to succeed at supplanting SNMP completely, but it's intriguing for sure. Okay, so we've provisioned our nodes, right? So once this XML document, by the way, this requisition gets slurped up into OpenNMS, you've got your nodes and you're managing them and you're doing stuff, right? That's it. So the next thing we have to worry about is service assurance. And as a reminder, that is the question, is it up or is it down? I got to speed it up a little bit. I'm running low on time. So there's not a lot to talk about in the service assurance realm here. While the controller does expose the presence or absence of your switches, like if a switch disconnects from the controller, it goes away from the list of switches that the controller gives you via the REST API. Also, if we're already pinging a switch and it goes away, then we already know that it went away. So there's maybe we could just tickle that API and say, hey, the switch that used to be here is no longer there, even if it's still pingable. Don't know how likely that is to be happening together. But really, besides that, most of the other stuff that we would do for service assurance, like pinging the nodes interfaces, and I don't know, maybe trying to connect with SSH to it for things that support that, which probably few will in the SDN future, it's better just to talk directly to the switch because we know already what its IP address is. So probably there's not going to be a lot of change. I'm looking into my crystal ball here in the service assurance concern here. Fault management. This is getting things like SNMP traps, right, to have the elements in the network tell the network management system about things that have happened that we're not polling for periodically. The controller can send unsolicited messages to a management system. This is pretty abstract. Like I said, Floodlight, in this respect, basically just logs stuff to disk or to syslog. But other controllers, I'm guessing, probably either send a trap, send a syslog over the network, or there may even be some kind of an open flow, like JSON callback kind of thing. I don't know. OpenFlow sends a port status change notification to the controller, right? So how does the controller get that to the network management system? Don't know. That's a big unknown in my mind right now, just because I haven't run into a ton of deployments in the field yet. But what these would look like, however they exist, at the abstract level, would be things like switch with whatever this DPID is, just join the controller, or this other switch never actually disconnected from the controller, it just went away and I can't reach it anymore, it didn't say goodbye, I don't know what's going on, but I should probably tell you about it because you're the management system that manages the network. This stuff's not really that well developed in the main, at least in the mainstream upstream Project Floodlight code base. I think what they're counting on is that the downstream OEMs that use Floodlight as the basis of their own products will implement this the way they want to implement it. So it'll end up being OEM specific. Anyway, regardless of how we get the messages in OpenNMS, we have a facility called the Event Translator that makes it trivially easy to reparent the data onto the correct node because given the data path identifier in the trap or whatever, we can look up which node that is, parent the event onto that node, and you're done. You can turn it into a notification, an alarm, whatever else you want to do. It's just part of the system now. So there's your fault management question. Last thing is performance management. And good news, Floodlight exposes a bunch of interface level metrics and a bunch of other stuff, but I couldn't really get much of the other stuff out of Floodlight, at least with the Open switches that I was playing with. We can collect performance data directly via a REST interface. We have a thing, it's actually called the XML collector, but anybody who's futzed around with XML and REST and JSON probably knows that XML and JSON are essentially interchangeable for many purposes. So our XML collector has a JSON handler that turns it into a JSON collector. I could write collection definitions today that would collect stuff from a Project Floodlight controller once we have the nodes in. So that's trivially easy. And even easier than translating the events that would come in via traps or whatever other transport, we can very trivially reparent the collected performance data onto the correct switch node. So this is what the port details end up coming out looking like. So in this output, this is for all the ports on the Zoe switch. This is port 1. We've got a number for receive packets, for transmit packets, for receive bytes, transmit bytes, drops received, drops transmit, error receives, error transmits, receive frames, receive overruns, receive CRC errors, collisions. This sounds a lot like stuff that's in the if table and the fx table, doesn't it? So we can collect this stuff directly via JSON, in theory. Not hard to do. I could go do it this afternoon. If somebody wanted to pay me to do it, I would. But there are a few caveats to this. The biggest one in my mind is always the scalability question, because what we deal with mostly in OpenNMS is very large networks. And I think the scalability of this REST and JSON mechanism to really large networks just hasn't been proven in the field yet. There just aren't that many really huge networks that anybody's trying to collect all this data from the controller on. So we'll see how that shakes out. Probably it'll be fine, but might need some tweaks over time. Also, most of your SDN switches that are on the market today still support SNMP. It's a legacy protocol. It's been around forever. Everybody supports it. Every NMS in the world knows about it. So my prediction in that regard is there probably will be a gradual transition from SNMP direct to the endpoint, to the controller API. Even with my little toy open vSwitch switches, I could just install the net SNMP agent on those guys and collect the same data from the if table and if X table that I would get from the API. Same stuff, same interfaces. For this to become a reality, the centralized collection of performance stuff, consistency across different controllers' API implementations is really going to be the key. So vendors, behave yourselves. Conform to the standards. End of lecture, but not of talk yet. There should have been something in here. I think this is supposed to be my conclusions. It is. I just don't have a big conclusions word up there. So yeah, conclusions, still really early days for SDN on the ground, at least outside the academic world. There don't seem to be a ton, well, okay, excepting Google, maybe, a ton of really homogeneous SDN deployments in the world. Most deployments that I've seen are hybrid. You've got some Nexus, but you've also got some iOS. You've got some Contrail, but you've also got some classic Junos, whatever. We've also had some practice in OpenNMS in dealing with similar kinds of shifts, so like the shift to virtualized servers from physical ones. We've coped with that by talking to the VMware vSphere APIs, very similar to what we're doing here with talking to the OpenFlow controller APIs. Anybody here works on SDN full-time? I think that's you. Mm-hmm. Yep. 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 So the big carriers love this stuff, and Google loves it. Mm. So the old school operators are excited about it until they think that they're going to have to forklift in this separate data and control planes and retrain. That's the catch, I think, is retraining all of your carbon-based units. Right. So it's hard to talk over you, but it's for the recording. So they're bringing in something semi-centralized, but still using OSPF and other routing protocols. Yeah, half pregnant, exactly. And that's how we ended up with Contrail. Yeah. Yep. So. Yep. So the operators, just like the OEMs in the space, see that they're going to need to do this stuff to compete, but it scares them a little or a lot, depending. So they're not getting fully in. The three of us will talk about how it helps the operators compete. I'm running out of time. Sorry. Yeah, it's not about the technology that makes the network go so much as the applications that the network enables and the business that those applications enable to function. That's what's driving the operators and the enterprises. Can we push that to after, because I'm really running out of time, seriously. So I just want to get through a couple more slides. It'll be question time, and we can actually take that offline. Cool. All right. So is SNMP finally dead? Maybe. Probably not. It sure has its problems. It's painful as hell to implement. Anybody who's ever tried to implement either an agent or a manager in the classical paradigm knows how hard it is. The SMI, the structure of management information that defines how you represent data in SNMP, isn't quite up to the 21st century, really, to be perfectly honest. It struggles when you try to model really complex relationships. You end up with weird tables that are joined to other tables, but there's no way to document those joins in the MIB because it's old technology and nobody thought about it, and they wanted to keep it simple when they designed it, so they did it this way. Also, when you get data out of an SNMP MIB, it's intrinsically stateless. So as you crawl through the data in a table or 2 or 3 tables that you're going to have to join together, it can be shifting under your feet and you won't even know it. So that's a big problem. There's no such thing as like an atomic large get, even if you're using get bulks. But even with all these problems, SNMP is still really, really useful. It's entrenched, it's useful, that makes it durable, so I don't think it's quite dead yet. Questions? Yep. So when would a small to medium enterprise be in a position to move over to a software-defined network paradigm? Depends on whether they want to build or buy. If they're in the mood to build something, they can do that today. To buy, I think it's coming. I think it's largely here. I mean, there are a lot of players that are doing OpenFlow in particular. It's starting now. Depends on what kind of budget you're talking about, but I'm seeing more and more Arista networks, which is all SDN. I'm seeing a lot of Nexus, but again, mostly except really, really well funded, like in the high-speed trading space where they've got basically unlimited funds, or if you're a Google where you're a huge enterprise with unlimited funds. Larger cost, but if you want to build, it's all commodity stuff. Customizable, yeah. Yep, larger cost but customizable, yes. So the question is, not a lot of huge deployments. Are you asking me to define huge in terms of like deployed switches? In my perspective, I'm seeing networks that have tons of nodes attached to them. I'm speaking specifically about software-defined networks that have tons of servers, tons of leaf nodes on them, but very few switches. Density really seems to be increasing along. I think it's probably not directly tied to the shift to software-defined networking, but density of ports seems to be really ramping up too. So you're seeing fewer switches in a software-defined network doing the same job as more switches, routers, firewalls, and stuff in a traditional network. So it's actually easier to manage these networks to a degree, even if your network management platform is not specifically SDN aware, because the switches still kind of look like traditional network kit. Yeah. So if you want to build your own network, you still need to buy some kind of hardware. Yes. Where do you buy the hardware from? I don't know. I'm not in a position to endorse a vendor. And who are the main players that would sell you SDN stuff? I think Arista is a big one. I'm seeing more and more of them. Somebody said Cumulus. I don't know how affordable they are. Honestly, I'm vendor agnostic in this debate, so I'm not going to make any recommendations. I'll just tell you what I've seen in the field. Yep. Got another question? How do I see software-defined networking changing both the design of the network and the process of both the design of the physical network and the process of network design? I haven't been inside a process of designing an SDN yet, so I don't know. But I have a feeling that it's probably more systems thinking, probably starting to look more like a DevOps team and less like a traditional network engineering team. And by saying DevOps, let me just go ahead and say System D, so I hit like all the controversial terms and buzzwords in one talk. I think I've got time for one more. Yeah. One more time, please. Are any cloud computing providers going to SDN? I don't know. Does anybody know that? The answer to that is Amazon running on SDN? Most of them are running overlay networks. Yep. So playing off of his question, do we think that the overlay technologies are going to speed up adoption of SDN or slow it down? Don't know yet. That's for speaking only for myself. I just don't know yet. All right. Well, thank you all for coming out and for your attention. Have a great afternoon.